morning, Lois Gray from North Island College. I don't know if anybody's dialing in. This is Control and Instrumentation Week 3. Yeah? Okay, so last week was probably your worst mathematics week because we were looking at actually building the models from first principles. We looked at an RLC model and we looked at a mass spring damper model, and I showed you how to use the first principle differential equations to build those, to build a mathematical equivalent of those. And then we also looked at Laplace transforms, which simplified the equations to make them more like linear equations. And then from the linear equation you could get a transfer function, which, if you remember, was output over input equation. Yeah, and then you can then put that into Simulink as a block diagram. So everybody okay with that? There was one little wee bit I was going to just finish off with you that I didn't do last week. That's quite common with the electrical one. I'll just do that just now. So, just grab my notes so I don't write the wrong one down. I don't want to do it from scratch again. I'm trying to remember what the equation was. But anyway, I think we ended up with an equation for the electrical one. I better get it. I don't want to write the wrong equation down. Have you got it handy?
No, I remember it.
You can remember it, that's really good.
That was RC.
Was it RCS?
Yeah, and then I squared
Plus
C.
S squared LC?
Yeah.
Oh. Okay,
Yeah.
don't copy this because this might be wrong, but I'm just going to plus 1, something like that. No, that doesn't look right.
Yeah, I kind of.
I don't want to have to do it from scratch.
I've got one that says on the line below it.
I don't know what this
No,
is.
that one.
What
I
about
plus
no?
ALS.
It's
the last bit's wrong, isn't
SC
it?
over
C.
SC over all of that.
SC over all of that.
Yeah,
Aye.
Okay, yeah, that's fine. That makes sense.
I tried.
That was pretty good. It's quite interesting. Remember the bottom part. Okay, so that was for working out the current. Sometimes what you might be asked, I mean, you could be asked anything really, but sometimes what you might be asked for is how the voltage changes across the capacitor instead of the current. And it's quite easy if you've got the transfer function of the current. The voltage across a capacitor is equal to the impedance of the capacitor in the Laplace domain. Remember, I showed you two different ways of doing it last week. There was the way with all the differential equations, and then there was another way where you actually just transformed the. Sorry, I did that wrong. That should be R. You did the transformation before you wrote the equation. Yeah, so we did it two different ways. It works either way. But if you do the transformation before the writing of the equation, you end up with impedance values that look like that, with your Laplace variable S. And then you know the voltage is the impedance times the current in the Laplace domain, not in the time domain. So you can easily get a transfer function for VC over V if you wanted to know how the voltage across the capacitor changed by just multiplying by 1 over SC. Yeah? Because that was current. And to get from current to voltage, you multiply by 1 over SC. Does that make sense? So then these cancel out and you do just end up with 1 on the top line. Okay, does that make sense? That's maybe an easy way. I think in the notes it shows you using... Well, I can't remember how it does it in the notes, but it's got a more complicated thing. Oh yeah, I think it does it like that. Which you can also do, but that's going back to using the differential equations right at the beginning. So you can do it that way as well. So that would be when you got the first equation, the differential equation, replace all your I terms with that C dVc by dt term, and you'd get back to the same, you'd end up with the same answer. Okay. You can have a look, that's in your notes anyway, so that's easy enough. Right, I need to roll that. Okay, so today In fact, let me ask you, what's the point of doing all this? Is it just to give you lots of difficult maths at a degree level? Sorry, sir?
Design a control system.
To design a control system. Well, what's the point of doing the maths though and making the models?
So that you know it's going to work really well.
Yeah, so that you can do a lot of tests on a hopefully accurate mathematical model and see how your system's going to respond. Make sure it's not going to do something like Tacoma Bridge and oscillate and kill it and destroy itself. Yeah, so that's the main reason for doing this. So today we're going to look at system responses and how, if you put a step input into something, what you would expect a different type of system to do, different systems to do. So you get first order systems and second order systems. You do get higher order systems too, but we're not going to cover them. You're only going to be interested in first and second order. So what's the difference between first and second order systems?
First order has feedback.
No, that's not the difference. Any order of system would have feedback. I did tell you this.
Store energy.
Yeah, good. Yeah. So first order systems only have one component storing energy. Second order systems have two components storing energy. Okay, is anyone brave enough they want to go and draw a first order system response on the board for them? No? You've done this in HND level, most of you. I know some of you maybe haven't done this in HND, but most people have. No? No, you're confident enough to draw a first order system response to a step input? Yeah, if you have to look up your notes, it kind of defeats the purpose. Okay, so time normally would be seconds. Amplitude obviously depends on the system and what we're doing. So what we're going to do is going to put a step in, say at time 0. And if it's a first order system, it will have a defined response that you kind of should know. Yeah, like a sort of logarithmic type of curve. Yeah, good. So you could have drawn that.
Yeah.
Yeah, so it's going to have a response like that. And there's certain features about that response that are always the same for every system, if it's a first order system. So along this axis there's a point, let's call that the final value. Okay, so the final value might not necessarily be the same as the red line, but it's the point at which the green line stops, the output of the system stops changing, yeah? So the red is the input, the green is the output. Okay, so what do you know about, say I pick a point here, and I call that tau, which is the time constant of the system. What amplitude have I reached by the time I get to the time constant?
63.3%.
Or 2, yeah, around about that, 63. I think it says 2 in the notes, so we'll stick with 2. It might say 3 sometimes. Close enough anyway. Okay, that comes about by the equation of that graph, actually, in that the final value, I'm going to call it voltage because I'm used to using voltage, but the final value is equal to the, no, sorry, that's wrong. If you look at the voltage at any, or the amplitude at any point, let's call it A, in fact, A for amplitude. Makes more sense for a mechanical flow. Is equal to the final amplitude times 1 minus E to the negative T over 2. Okay, so at any point, that actually equation equates to that 63.2. At any point, like say I wanted to measure the amplitude at that time, all I would need to do is put in all my values in there and I would get the value of A at that time. Does that make sense? We should have done this before, I think. Is there anything else we want to know about that? I think there's some stuff in the slides that tell you a bit more about that response, so we'll go to the slides in a wee minute. But you've seen that before? Everybody's seen that before? Yeah. Right, okay. 2 people are just noting it down. And this applies to mechanical or electrical systems, doesn't really matter, or hydraulic, pneumatic, any first order system, really. See if you remember anything about second order systems as well. Okay, finished writing? Carry on. So second order systems are a bit more complicated. You probably know that already. Certainly the maths is more complicated. So again, if we put a step in, I don't know what colours I use, but I'm going to blue. Okay, you might actually get the same response from a second order system. You might get something similar, but you can't do the same sort of things with time constants and things because it's not exactly the same. Well, is that the only kind of response you would get from a second order system? No. So what other kinds of responses can you get? In fact, would you know what kind of response that would be, what that would be classed as? Overdamped. Yeah, good. Is that what you said?
Yeah.
Yeah, so that green one's an overdamped response. Damping is the process of taking energy out of the system. So overdamping means you've taken more energy out of the system than you maybe want to, or you've just made sure the system doesn't have enough energy to do the opposite of overdamping. So what other responses do you get?
Underdamped.
Underdamped. What does that do?
Overshoots and then
oscillates
to get to a steady state.
Okay, so you get underdamped. Of course, they might not all reach this final value. So that's underdamped. Good. Oops, spelled that wrong. Okay, any others?
Critically damped.
Critically damped. What's critically damped system do?
So almost straight away to the final value.
Yeah. So our critically damped system's your ideal system, really. It's going to rise really fast to its final value, which is normally what you want. You normally want your system to respond fast. And then it's going to pretty much settle at that final value without really overshooting much. I think most people probably remember this, so that's good. And what colour have I not used today? It might do something a bit like that. Maybe not quite as big a peak as that, but something along that lines anyway. There is actually one fourth one which you might not have come across. Okay, what if there's no damping in the system whatsoever? What's the response of the system going to do then? If you're not removing energy at all. It's not really a realistic situation because in real situations there's always some energy being removed by, well, wire's got resistance. In a mechanical system, what's the main ways that energy gets removed from a system?
Heat, vibration.
Heat, friction, yeah. There's always some kind of slowing down force or reducing force. So there's never, you never really get systems that don't have any damping at all, but in mathematical terms you do, so we do have to think about them. What do you think a system with no damping at all would do?
Would it just overshoot and settle on, like, above the set point?
It doesn't settle. You're right, it does overshoot.
Surely it would reach a finite value.
No, if it's got no damping, it will oscillate forever. That's definitely
Yeah, but
having no
it
damping.
wouldn't continue rising, surely. That's what I mean.
No, because there'll always be some limiting point. Now, why would there be a limiting point? Well, it's limited by the amplitude of the input you put in for a start. You know, the system's not going to infinitely increase forever if you've got a limited size of input. There's also usually other limiting factors. What an undamped system will do, we'll just do that forever. So that's kind of like what the Tacoma Bridge did with the input that it went into. And I get, yeah, you're right. I mean, it did go to very extreme amplitudes, but there is always some kind of factor, usually the input. So that would be undamped. Okay, so what we're going to do today is look at some of the mathematics behind this and how you can tell from your model what the system is doing. And that will also tie in with your coursework as well, because with your coursework, the easiest way to derive the system transfer function is to work back from the fact that you've got a step response output. What sort of system is that? And then work back to the parameters that define that system, rather than trying to model it piece by piece. Okay? This is just a wee bit of revision. Good. Okay, I'll just switch over to the slides, I think. Yeah. Good class today. Good. Right, slides. Is anybody still copying that?
Catch up from last week. No. Sorry.
Okay, so this is related to chapter 4 of your book, so we've kind of skipped chapter 3, I think. Why did we skip? Oh yeah, because you're not doing state space, and chapter 3 is about state space. It's a better way of analysing the systems, but I don't think your maths prerequisite is enough, so we're going to skip chapter 3 and go on to chapter 4. Okay. So there's a few different ways of defining systems, whether they're first or the second or the third or whatever. One of the ways is to look at the transfer function and to determine whether it has so many poles or so many zeros. Have you heard of poles and zeros? No. Okay. So when you get your transfer function, it's an equation, yeah? If I just skip back. In fact, previous one. No, that's not a good one. I'll put an example up to make it easier. So we're talking about transfer functions in the Laplace domain. Generally output over input. I suppose more correctly it would be control. Control variable over reference variable. And then you might get something with s's on the top and something with s's on the bottom, yeah? Or s squareds or whatever. So if you factorise that into and so on, where a, b, c and d are numbers, yeah? And s's are your Laplace variables, they stay as s's. The definition of poles and zeros is what makes that transfer function infinite or zero. So we've got poles are the values of s, which makes the transfer function equal to infinite, yeah? And then we say poles are values, s values which make obviously infinity is not a real number, so I've got to say 10 to infinity, not actually infinity. Okay, so if you have an equation A over B, what in that equation could make that infinite? Yeah, what could you set A or B to make that equation infinite?
Zero.
Which bit would you set to 0?
B.
B, yeah. So if you want that to be infinite, you would set B equals 0, and then that would tend to infinity. The whole equation would tend to infinity. Yeah? So it's exactly the same with your transfer function. To make the transfer function tend to infinity, you set your denominator to 0. So you find all the values of s that would make the denominator equal 0. So for instance, in this equation here, what value could I make s that would make that bottom line 0? This equation here.
Negative C.
Negative c, yeah? Or
Negative D.
negative d, yeah. So hopefully you can see that's actually the roots of that equation, yeah? S equals negative c or negative d would make that tend to 0. And the other thing is that, so that's poles, and then the other one is zeros. Zeros are a bit easier to understand. Same idea, values of s. I think this is on a slide anyway, so I don't really need to write on this. Transfer function equal to 0. So again, looking at that top one there, what values could I use for s that would make that 0? Someone other than Robert. If I wanted this to be 0, this equation, what could I make hence? Yes, it was a trick question, too easy for you. Yeah. Okay, so in this case that would be s equals minus a and s equals minus b. So for this particular equation, that's just an example. I've got 2 zeros and I've got 2 poles, and they actually define how the system will respond to various inputs. We can use them instead of just our knowledge of first and second order systems. So the first bit of the slides are to do with that. Maybe a few minutes because some people are still writing stuff down. And actually, this is more powerful than probably some other ways of working out what a system's going to do. Knowing the poles and zeros can give you a better estimation or a more accurate estimation. So if we go back to the slides. So that's basically what I just told you, yeah? Poles are the values of the variable s that cause the transfer function to be infinite. You don't need to worry about this bottom bit, to be honest. You're not really going to come across equations that have those bottom bits. So just those bits, that's all you need to know. And you can draw a pole zero diagram to see where the poles and the zeros are. And from the pole zero diagram, again, you can determine how your system's going to respond. Okay, so this is an example of a pole zero diagram. This y-axis is an imaginary axis, j omega, and this axis here is a real axis, yeah? As with normal diagrams, that's plus j omega, that's minus j omega, that's plus, I forgot that symbol, I think it's delta, and that's minus delta. Right, and every system is made up of the thing that you put into the system and its own transfer function. Okay, so your input has a transfer function, and a Laplace transform, and your system has a Laplace transform, and the response will be determined by both of those factors, not just one by itself. So, for instance, in this system here, this is the actual system transfer function. I hope you can see that. And then what we're putting in here is input that has a Laplace transform of 1 over s. So does anybody know what kind of input that is? We did look at Laplace transforms last week. So in terms, is that a ramp? Is it a step? Is it a parabola? Did you say step?
Yeah.
Yeah, that's a step. That's a unit step, actually, because I can see the value of 1 up here. So if you were to do the Laplace transform of a unit step, that's what you'd get, 1 over s. Okay, so we're putting a step input into this system, and we're going to analyse what we get. So you can see here we have a 0 at minus 2, because if you make s equal to negative 2, that top line becomes 0, so that's what this bit here represents. And we've got a pole at minus 5. Because if you hit the bottom line minus 5, you get infinity, and that's your pole there. And that's standard representation. Poles are crosses, and zeros are circles. The zeros are easy to remember because they look like zeros, yeah? So as long as you remember one, you remember the other. Okay. So this is the total response made up of the entire thing, the step input and the system. You've got to know a wee bit about partial fractions, so I was actually going to just quickly show you this as well. Have you done partial fractions in maths?
I remember
Yeah.
a bit.
Okay. If you have done it, it'll be a bit easier. If you haven't done, then that might not be so easy. But... So with that system, I'll just show you how that works. It's not that difficult with some of the stuff we've done so far. I've this written down somewhere. Here we go. Yeah. So if we wanted to look at that system's response to a step input, we're looking at an entire system which has the transfer function of the system, and we're multiplying that by 1 over s. So that's our entire transfer function there. Just make that like that, yeah? So we want to split that into partial fractions. Let's just rewrite it a bit more tidily. And you could almost think that we're obviously going to have a number over s plus a number over s plus 5 if we wanted to split that into two fractions, yeah? So we just say a number that we don't know what that is. A different number over s plus 5. Would you agree? That's quite easy to see, I think, from that, yeah? So obviously, your bottom line, when you do fractions, think about fractions, if you do a quarter plus a third, the bottom line becomes 12, becomes the multiplier of the two, yeah? So that's how that works there as well. So what we want to do is, using that right-hand equation, I'm not sure how to explain this, but put a common denominator down, which was obviously the thing that we were looking for anyway, and then see what we get on the top line. So we've got a over s. If you remember your fractions, you divide the bottom line by the denominator s, and then whatever's the remainder would multiply by a. Does people remember doing that sort of thing? We'll do it with a... do it with a fraction first, plus, I don't know, 2. Yeah, so what you do on the bottom line is 3 times 4, okay? And then you would divide 4 into 3 times 4 leaves 3, so you'd have 3 times 3 on the top line, and then 3 into 3 times 4 leaves 4, so you'd have, I don't know if you remember doing that in fractions, but that's the way you normally work out fractions. Probably years since you've done this, primary school. But you get the idea? Yeah? Okay, so you can do the same even though it's letters, it doesn't really matter, letters and numbers are pretty interchangeable. So this one we'd say s times s plus 5 divided by s leaves us with s plus 5. Yeah, so on the top line we've got the multiplier a, and then the remainder, which was s plus 5. And then on the bottom line we've got s times s plus 5 divided by s plus 5 leaves... What's the remainder of that? Dividing that by that. S. Yeah, good. Okay, so that leaves s, and we've got a multiplier on the top. B of s. Yeah? So you end up in the bottom. The bottom line obviously is correct already. The bottom line does already equal that. So what we want to do is find the values of a and b that give us this top line. Yeah? Because what we want on the top is just s plus 2. We don't want like a times s plus 5 plus bs. So, from there on, it's just a matter of doing a little bit of simple maths. So what do we want the top line to equal?
S plus 2.
S plus 2, good. So the easiest way to do this is to pick some values of s that make some of these terms disappear and then find the answer that way. So to make this first term disappear, what value of s could I use there? Minus 5, yeah. So am I going too fast? Are people okay? If you've done it before, you'll probably find it quite easy. So for the first thing I'm going to do, I'm going to make s equals minus 5. Okay, which means that first term disappears because you've got a times 5.
Result, that's good.
What's wrong, John?
What's that?
What's wrong?
Just saying it's magic.
Plus b times s, so it's going to be b times minus 5 because we've made made s equal to minus 5 equals minus 5 plus 2. Okay? So this first term is going to be 0, because minus 5 plus 5 gives you 0. Yeah? And this second term is going to be minus 5b equals minus 3. Yeah? Okay, and then if we divide that out, we end up that b equals 3/5. Yeah? Okay, maybe I'm going a bit slow for some people. So b is going to be 3/5. So if we scroll back up to the top, we had b over s plus 5. So one bit of our fraction is going to be 3/5 over s plus 5. Okay, but we haven't found this first part yet. It's a bit untidy, but hopefully you're still following. Do you need this to stay up for a few minutes?
No.
Okay, you happy with that? Okay, so we do the same to find a. So what value can we make s? Oh gosh, what happened there? I think I zoomed in and I didn't need to.
Oh, carry it there.
Start again.
Will it matter? You can still see it, can't you? It won't matter.
Oh, you can look.
Okay, for the second bit, we want to get rid of the b part, so we're just left with a. So what value would I make s to get rid of that b bit?
0.
0. So if we make s equals 0, we're left with a times 0 plus 5 equals 0 plus 2. Would you agree with that? Yeah, and just by a bit of arranging, we've got 5a equals 2, so a equals 2/5. Okay, and that then gives us our other bit of the equation here. Just draw a line. So that's essentially our answer to that equation, yeah? That should have been a 5, by the way. My s's and 5s look quite similar. Okay. We should make that more square. Get the idea. So 2/5 over s plus 3/5 over s is the separation of that equation that we had at the top. Okay, we can have a look at this later. I don't know why that moved over to the side. So essentially what we've done is split up that equation into two separate equations. That's your partial fraction. Most people will have done this at some point, I think. Okay? If you followed it or not, but hopefully you'll get the video later. So anyway, that's what was done on the slide. Is anybody still writing? So if we go back to the slides again. That's what they've done here. Okay, so that's the answers we got, yeah? See those two answers there? And then they've done the inverse Laplace transform. Now, I wouldn't suggest that you need to be able to do that. You'll get a table, if you were asked this in a test or at any time. You'll get a table to do the inverse transform. But the way it works is if you just have something over s, that becomes the constant times a unit step, which we already worked out earlier. So that just becomes 2/5. And this bit, because it's got s plus 5 on the bottom, becomes e to the minus 5t. Okay, but you can always get that from an inverse Laplace transform table. And that's made up of a forced response, which is the thing you're putting into the system, and the actual system's own response, which is this bit here called the natural response. Okay, so I'm just showing you the pole zero plot of that complete, I think, is on the next page, and it's not. Okay, so this would be a complete pole zero plot. You'd have the pole at 0 due to the step input. You'd have the pole at minus 2 due to the 0 at minus 2 due to the numerator, s plus 2, and then the pole at minus 5 due to the denominator, s plus 5. I think that's quite straightforward. Yeah? Okay. So here's some more examples. Telling you what will happen with the different types of poles and zeros. So if you have a real pole, so this is on this real axis, not on this imaginary axis, what that causes is it causes a inverse exponential response, like the ones we've been seeing earlier, yeah? Which would be just your sort of rise like that. So if we look at a first order system, the transfer function of first order system is going to be something like the form here, where a is a number and s is your Laplace transform variable. And that's always going to have a real pole at this denominator value when s equals minus a. So that's for any number a. Yeah. So we know already that that has a response like this. We looked at that right at the beginning of the lesson. So looking at first order systems, we've kind of already done this today, so I think this will be quite easy for you. The standard equation for any first order system is of this form here. where k is the gain of the system, so that's multiplying the amplitude of the step to reach a final value, or dividing the final value by the input value, that would also give you k. Tau is your time constant, which is your 63.2.3% point, when your amplitude has risen to that, your output's risen to that point. And that's about it, really. And so you can always work out what your system's going to do if it's in that form. So for instance, this system here, what's the gain of that system? 1? Yeah? So we'd expect the output of this system to reach the same value as the input eventually. Yeah? It's going to rise, it's going to do a sort of inverse exponential, or it's more like a logarithmic rise, I suppose, to this final value given. Yeah? Because this is 1. What's the time constant? RC?
RC.
RC, yeah. So it'll reach 63.2% of 1 in time R times C, whatever values of R and C you have. Yeah? I think that's quite straightforward. Most people will have seen this, yeah? Stop me if I'm going too fast or if there's something you don't understand. I've already told you all that. I'm not sure what it means by definition the input should be a step, but we're looking at responses to steps for these systems, so let's get through that, I think. And that's just telling us what we already looked at before, that the response of a first order system is the input plus the system's own response, which is this thing. Okay, never mind that, I don't really need that. Okay, yeah, you guys can have a go at this. So for these systems, I want you to work out what the gain value is and what the time constant is. I'll just draw for you the standard function so you can rearrange it. So I want you to find k and tau. It should only take a few minutes, it's really easy. You can do a little bit of algebra first, as a clue. If anyone was really clever and printed the slides off before they came, I'll have the answers.
I would just be cheating. Shell was really there.
You think? Okay. Could be called preparation.
We'll learn that way.
Next weekend.
Okay? Done that?
Right.
Shouldn't take as long as this. Okay, I think that's long enough. Anybody want to tell me what K was for the first system? No, nobody wants to tell me that. Right, I'll give you a wee clue. All you need to do is divide everything by 5 to get rid of this 5 here. So it's as easy as that, yeah? So you divide everything by 5. 5 divided by 5 gives you 1, so k is 1. Okay, you'll probably do something a lot more complicated. That becomes a 1. What's the time constant? A fifth, yeah. So it's as simple as that, yeah? Okay, so bottom one, same idea. K still be 1. The time constant this time will be 1 over 20, yeah. Simple as that. I don't know what you were all doing there. Now you know how to do it. Oh, they got 0.2, but same thing. Okay? So that's a little bit of algebra that is just wee tricks that you need to know how to do. Yeah, without thinking about them. Yeah. So it asked for the forced response and the natural response, but the forced response in each case is a step. So there's 1 over s term here. Okay. Any questions? Are you okay with that? Yeah. You probably did something really complicated. But there we go. Okay, that we've already looked at, so we'll just skip over that. I suppose the only thing that might be of some relevance is that this settling time for a first order system is defined as being approximately 4 time constants. Okay. And then there's a few equations. You wouldn't need to remember these. You can always get them from a book or something. But so if it's an inverse response, so this is the response that does that. But sometimes it's a decaying response which does the opposite. You know, goes like that.
Say that again?
First order systems, it could have a rising response to a step, or it could have a decaying response, depending on what type of system it is. So,
do you have an example of a system with a decaying response?
the voltage across an inductor, when you apply a step voltage change to it. Yeah, you think about inductors. They have a big voltage at the start when you first pose the switch. If you think of a circuit like this. In fact, no, make that easier. Okay, so when you first shut that switch, there's a big volts across there because that's your back EMF, and then that gradually dies away to nothing. Yeah, that's probably the best example. I can't think of a mechanical one, but I'm sure there are mechanical ones as well. Anyway, so there's a slight difference, obviously. The time constant's at a different point there. It's 32.7% or, yeah. In fact, it won't be final value in that case, would it? It would be initial value. Final value is 0, so that would give us like half initial value. Where that would be your initial value. And certainly with electrical systems, you usually get current and voltage doing the opposite thing. So one will have a rising response and one will have a decaying response for each system. Yeah. It's like the transient responses. If you did DC and AC principles, did everybody do that? No, you maybe didn't.
Say that again.
DC and AC principles? No. As a unit. You do things about inductive and capacitive transient responses. This is just the same theory. It's talking about the same stuff. Yeah. Okay. Okay with that? So, yeah. So it's the time constant's the time for a decaying response to be 37%. It's actually 37.3, I think. For a rising response to be at 63%. Then you've got the rise time is nearly always defined as the 10% to 90% of final value. Not always. Sometimes it's defined as 0 to 100%. But most systems it will be defined as 10 to 90%. And that's approximately 2.2 time constants. And then settling time, we always have a finite limit whereby we say the system is settled. And that's because some systems will never settle. There'll always be some noise in the system and there'll always be some small oscillations. but to all intents and purposes, the system's reached a final value. It's not really going to change drastically. So we normally have a 2% tolerance on the final value, and we say that's the settling point. Do you understand what I mean by that? Yeah? Okay. I don't think we'll bother doing that one because it's just the same as what you've been doing already. But the idea is you rearrange that so you end up with a formula of s plus 1 on the bottom. So again, the gain of this system's 1, the time constant's 1 over 50, and then you just plug in these numbers into these equations to get those other values. So just skip those. I'm not going to make you do that. But so we have the time constant is 0.02, which is 1 over 50. The settling time's 4 of them, and the rise time's 2.2 of them. It's quite straightforward, quite easy. Yeah. All that. Any questions about that? Just because I say it's easy and you've got a question, don't feel that that's a bad thing. It might just be that I've explained it badly. Okay, we're going on to second order systems now. So the first order systems always have that standard transfer function k over s times time constant plus 1. Second order systems always have a transfer function in this form. Now it might not look like that when you first get your second order system transfer function equation, but it's always possible to put it into this sort of form. Now, where each of those terms has a meaning, k again is the gain, which may be a loss, and in fact for most systems is a loss. It's a multiplying factor. How much different is the final value of the output from the input that you put in? So you've got k, they call it gain, but it's usually loss. Omega n is the frequency at which the system would oscillate continuously if it had no damping, and that's in radians per second. S is your Laplace transform variable, so that doesn't really mean anything. And this strange sort of symbol here, zeta, which I'm really bad at drawing, by the way, is the damping factor. Okay? Or we call it damping ratio there. Okay, so this form isn't really all that useful in terms of a pole zero diagram. It's great for finding out what your damping ratio is. It's great for finding out what your frequency is. It's great for finding out your gain, but it's not brilliant for finding out your poles. There's no zeros in this system because there's no s's on the top line at all. But to find our poles, we'd need to factorise the bottom line here, and that's essentially what's been done here. I wanted to show you how to actually do that as well, though, because it involves a wee bit of complex number factoring, which you might have to do later. So I'll show you that too. And basically, that is the factor of that. So if I just switch back over to mine, will I wait for you to come back?
No, it's
I'll
really
just carry on here. So have you done the quadratic formula? I think that's what it's called.
Yeah.
Yeah, okay, so that's how they do this factoring. You'll have to ignore my terrible computers. I'm really bad at formula. Okay, so that's our denominator. Yeah? And normally to find our poles, we would do negative b plus or minus the square root of b squared minus 4ac over 2a. Right, you will not get that formula in an exam. You're expected to know that. You should have been doing that for years by now.
She used to do that in high school.
Yes, okay, so that's good. Okay, so if you can tell me what's b in this equation? What's b here?
The middle value.
The middle value, which is
Two.
the variable's s, of course. So it's all the constants in this equation, not the variables. So yeah, go on to
that letter.
Zeta, yeah.
Yeah, zeta, that, the frequency, the natural frequency.
Yeah, that's it. Good. 2 zeta omega n. Yeah? Okay, A. Anyone want to tell me what A? Use a different colour.
S squared.
What's A?
S squared.
No, S is a variable.
Ah.
It's only the constants that are A, B's and C's. 1?
Root square.
1?
Oh.
A is 1. 1 times S squared gives S squared, yeah? Okay. And C?
Natural frequency.
Natural frequency
Squared.
squared. So then it's just really a matter of putting the A, B's and C's into the equation. Not really difficult, to be honest. So we've got negative B, so that's negative 2 zeta omega n plus or minus the square root of B squared, which is going to be 4 zeta squared omega n squared. Yeah, so that's that B, every term in the B squared, yeah? Minus 4 times A times C, which is going to give us 4 omega n squared, I think. All over 2. Bottom line, so it's easy because it's 2 times 1, which gives you 2. Yeah? And then we can take certain values out of the brackets. You can multiply. You can take out factors that are common to both terms, just like you do with normal brackets. This time it's a square root sign, but it's the same idea. And that being on that side, and I don't know why it ended up on that side. Okay, so 4 is common to both, so we can take out the square root of 4. The omega n squared is common to both, so we can take out the square root of omega n squared. And then we're left with zeta squared minus 1. Yeah, and that whole thing is still over 2, yeah? You should have done this in maths, I think, at some point. So square root of 4 is 2. Square root of omega n squared is omega n. And that's still over 2. And then just the final bit is divide everything by 2, so we end up with negative zeta omega n.
It's actually easier.
Plus or minus.
Just overthinking it.
Square root of. Which should have been the answer that we get earlier. So again, algebra more than anything else really, but I did tell you need a lot of algebra for this course. So. I'm hoping that's the right answer. Somebody can tell me whether that was the right answer.
Yeah, it looks right.
Yeah. Okay. Oh, sorry, that last bit should be zeta squared. Yeah. It was zeta squared here, I just forgot to put the square on.
Yeah, that's how it written.
It does make me wonder if you're actually following everything I do.
I just thought you had it analysed. I didn't think.
Oh, right, okay.
It's not there.
Okay, so that's just the way you factorise those denominators, and you probably won't be doing it with, you won't be doing it with zetas and omega n, you'll be doing it with actual numbers, yeah? Which is easier.
Yeah.
We'll do 10. That's fine. I think we're doing okay. We haven't that much more to do in this, I don't think.
See, no.
So of course this equation here is the standard factorisation for any second order system. Yeah, you would always be able to get it into that form by poles. Okay, shall I carry on? Right.
You scroll up a wee bit.
Yeah.
Closer to it.
Yeah, that's me.
Just to the original equation. So what you were doing was factorising that original equation there, which was the denominator of your transfer function.
That's fine now.
Okay?
Yeah.
Back to the slide again. Okay, so there you can see that's all they've done there, but they did it in one step rather than lots of steps.
What is that 1.2?
Sorry?
What is that 1.2?
Oh, this thing here, S.
S.
That's your values of S that give you 0 in your denominator. The 1.2 doesn't mean anything, it's actually 1, 2. Right, so it's the first S value and the second S value that give you the poles.
Right.
Yeah. Okay, we already talked about that. I think you already probably know this, that if your zeta value is less than 1, you have an underdamped system. If zeta value is equal 1, it's critically damped. If it's greater than 1, it's overdamped. If it's 0, it's undamped. Okay? And again, the system doesn't actually oscillate at omega n radians per second. It actually oscillates at a value a bit less than that, determined by, what is it, a bit more? I'm not sure. I guess it depends on what zeta is. Determined by the damping. And all systems have some damping, whether it's friction or resistance, or I'm not sure what else there is, but actual dampers in mechanical systems. Again, you don't need to remember these sort of formulas. You would be given that. And I'm not meant to be teaching to the exam, but just so you don't panic and think, oh, I've got hundreds of things to remember. You don't need to remember that. You do need to remember this and the first order form. Okay. You want me to wait, Mark? Are you okay?
No, right.
Carry on, right, okay. So, now they've done a few steps here, but the first thing they've done, I wonder if I can do that, so it might be easier. Or do we need to bother doing that? In fact, we won't bother doing that, it's too complicated. We're just going to miss that. You can just believe me that function gives you this sort of response in the time domain. You don't need to do something as difficult as that, so I'll miss that one, I think. Right, this is a wee exercise for you guys, and I think you should find this quite easy. So what you want to do is compare this equation to your standard second order equation and work out the values of zeta and omega n and k if the k is something other than 1. Okay? And then you can tell me if it's underdamped, overdamped, or critically damped, or not damped. Okay, so I'll write the standard equation because we haven't had time to learn it yet. Okay, and a little clue is start with that term, okay?
Start with that term.
Start with that term.
No worries at all.
So if you can work out what omega n is, then k is quite easy to do. I'm sorry, omega n squared. K is quite easy to do, and omega n is easy to do, and zeta will come.
I'll easy Lewis.
Just relating each term to the... Is there anybody completely stuck on how to do that?
No.
You can admit it if you want. No? No? You're going to have a go? Yeah?
Yeah, that was too much.
So you have to go.
Okay.
Therefore, any help.
Forrest.
You're not in the video.
Turn the microphone off.
What's that? Turn the microphone off?
I'm only joking.
I'm not.
Still joking.
That's pretty bad. See that? Credit.
Still joking.
What I'll do is get the answers for A first, and then before you carry on, in case you're doing it completely wrong. I think that might be a good idea. So if you just do A, then we'll carry on with the other ones.
Can that be truthful?
Yes.
Did you follow it?
100% true. Okay. Which one would you
Straight for answers.
Because she's calling to me.
Oh,
I should say this is quite a common exam question as well.
Is it?
That's
Oh,
quite
yes.
easy, a bit of an exam question.
I think I see this one with that. When you get married, I'll show you the way. Put it in the way.
Choose your quadratic equation person.
Have you finished?
Almost.
So this is right.
Mark, what we're doing is finding k, omega n and zeta for those equations, and then working out if it's overdamped, underdamped, particularly damped,
Right, yeah.
or not damped.
Just put it in that equation.
Wait, how do you say that?
He's going to be wild.
Oh, yeah. Wait, that's not.
Yeah, good guess.
No,
Yeah.
no, just saying.
You're on the John, but
Oh, am I?
it's B going to be
Oh, you're a big one.
See if you have a word in this, you go sort of
Just get the answers so people are finished and you can check your own, yeah? So we're just doing part A.
Yeah.
What did you get for omega n?
Omega n, I got 20.
20? Well, that sounds right to me. Okay. Well, that's radians per second. Probably should really use the units. K?
1.
Yeah, he's easy. And then zeta?
I got 0.3.
Is that what I got? I'm not sure. Yeah, that's right. So what kind of system is that in terms of damping?
Underdamped.
Under, sorry. Okay. Did anyone not get that? Or anybody not understand how to do that?
Alright, should we go over how you did it? Aye, that
So I don't know how we did that. Okay, so I said start with the omega n squared term.
Yeah.
So this term here
Yeah.
is your omega n squared term. Would you agree?
Yeah.
Looking at those two equations?
Yeah.
It's the only thing that doesn't have an s term on the bottom. Yeah? Oh, sorry. It should have been omega n equals the square root of 400. Okay, that's your first bit.
Right.
And then you know on the top line that k times omega n squared equals the top. Okay, so the only thing k could be there is 1.
Yes.
Yeah, 400 divided by 400 is 1, yeah? And then the bottom line you've got, I'm running out of space, but we've got 2 zeta omega n equals what? Looking at the bottom line there, comparing that equation to this one. 12? Just 12. Okay, the s's don't come into it. Okay, it's just this part here. So that's equal 12, so now we can put our values in. So zeta is going to be 12 divided by 2 times 20, which should give us 0.3, yeah? It's actually pretty easy.
Okay.
Yeah, I was guessing that some people might not have the method right, but the actual...
That's all we want, is just make
Once you've got the method, it's pretty simple. Okay, you can do the other 3 now for me then. Be aware that your equations might not always look, they might not be in that order, like you might end up with, if you do it yourselves and you get in a transfer function, you might end up with something like 12s plus s squared plus 400. So you need to be able to always arrange them with the highest power of s on the left-hand side to be able to compare them. We'll give you 5-10 minutes for this. 2 minutes.
Good.
You're probably thinking this is a lot of maths, it's a bit meaningless, but it's actually really powerful for working out how your systems are going to perform. It doesn't seem like that at this stage. But
It makes sense when you do it. Football matters, isn't it?
few people finished. Rest of you finished as well? Oh, okay. Most people would do it. Mark and Gary, you just like texting people rather than doing their entries.
I'm looking at a slideshow on the Blackboard on my phone.
Okay, fair enough. I'm going to show you it now. No, it's not on Blackboard, I don't think.
Presentation?
I don't think it's in there.
Yeah, it's
Is it on the next slide?
It's in Control Week 3
Okay.
PowerPoint.
Oh, the PowerPoint is, but I don't think the solution to these.
Yeah, no, I'm not. Solutions. I'm just going on my own pace if that's alright.
No, that's fine. Okay, I think the majority of people have finished. Who's still working? Are you still working? Yeah. Give you a few more minutes if you want. I think what I'll do, I'll give you the answers. I don't think they are on the next slide. I'll just give you the answers, and then you didn't get them, you can maybe ask me later or talk among your friends or whatever. So. So we have, in fact, do you want to tell me what song we're in? The second one?
30.
30, good, yeah. K is still 1, and zeta was...
1.5, was it?
Yeah, good, okay, 1.5.
Ah, it's over
So what kind of system's that?
Over down.
Overdamped, good. Get some marks in the exam anyway if you can do this stuff, so that's good. Right, class C, omega n was 15, yeah. I think K's 1 for all of them, so just leave that.
It's critically down.
Zeta is
Critically down.
1, yeah. Spot on,
Yeah.
good. Okay, and then D,
5.
omega n is
5.
5, yeah, good. Okay, K is still 1. What's zeta?
0.
Zeta is 0, so what sort of system is that?
It's oscillating.
Oscillating or undamped. Yeah, it's got no damping. Okay, undamped. Good. Like I say, you'll pick up, I don't know, 2 or 3 marks in an exam if you can do that. Not a lot, unfortunately. Better than nothing.
No, it's quite simple.
Okay, so if you didn't get those, are some people writing that down? You'll have to do it in your own time. But you can ask me later. Okay, carry on then. Okay, and then here's some examples of responses and transfer functions. They're a bit small for you to see, and poles, and what's going to happen with each case. So we've got the first one on the bottom here. When you factorise that, you get minus 1.146 and minus 7.854, which gives you two poles on the real axis here, and what looks kind of like a first order response, but is actually a second order overdamped response. Yeah. So poles on the real axis in the negative side of the graph always give you an overdamped response like that. This one gave us two imaginary poles, I think. How does that work again? How does that give us imaginary poles? S squared plus 2s plus 9. I want to try factorising that just to show you how that worked out as imaginary poles. Because you won't have been doing that much stuff with complex numbers recently either. Though you've done quite a lot of complex numbers, most of you. People who did the electrical last year have done quite a lot. So we had s squared plus 2s plus 9. Was that the bottom line, I think? Yeah, so we've got the poles are going to be at negative b and the square root of b squared minus 4ac over 2a. It's going to give us, what's b?
2.
2, good. Okay, b squared?
4.
4, yeah. 4 times a is
4.
4 times c,
36.
36. Yeah. All over 2, obviously, because a is 1. So carrying on from there, negative 2 plus or minus the square root of minus 32. Yeah? Over 2. So can you do the square root of minus 32? And try typing that in a calculator? No, that's not going to work, is it? But what you can do is you can use your complex numbers. Remembering that your complex number, j, or sometimes I, is the square root of minus 1. Yeah? So you could rewrite that as negative 2 plus or minus the square root of minus 1, or j, times the square root of 32 over 2, and then just carry on from there. You're not going to actually do it because it's just numbers from now on. But yeah, you get the idea? Okay, so you can always do that with the negative square roots, and that's why complex numbers are quite useful. It's just a mathematical trick, it's not real, but it does help you find your poles and zeros and things. So, is anybody writing that down?
No, I'm straight around it.
Right, okay. No, okay, back to- So that's where we got these two poles here. I'm not sure what the actual values are, but they've got a real number part and an imaginary number part on the y-axis here. And that gives you an underdamped response, like that. Then, if you have two poles on the y-axis, that's an undamped response. Okay, so this would give us two poles on the y-axis, I think. Yeah, because it would be the square root of minus 9, which doesn't have any real part, it's just going to be an imaginary part. And then this last one is two poles on top of each other on the real axis, gives you a critically damped response. Okay, so that's just some slides that just show you. Actually, I'll probably make that back into slide. Shows, so it's a bit bigger. You get the idea. You can have a look at these yourself later anyway. So you can always tell from a pole zero diagram how your system's going to respond to a step input. Yeah? To some extent. And if you're good at your Laplace transforms, you can actually transform it to the actual response, but you don't really need to do that. I'll just skip over that one because you've seen that one lots of times. Okay, so what you can actually find out from the pole zero plot is a bit more than just where the poles are and what response they're going to give you. There's certain aspects of the pole zero diagram tell you other things as well. But this is the real part of the pole. Obviously on your real axis, this is the imaginary part on your imaginary axis. I don't know why they put omega n there. I don't know if that's that meaningful. Let's skip along to a different one. That's just the same again, isn't it? We've seen that already. Oh, that's just included the damping ratio, but we've already covered that, so I think I'll just skip those. Yeah, so the length of this line is omega n, and I can't remember what theta is. I think theta is just an angle that you will need to find out in your second coursework, but we won't be using that. You can use this angle theta to determine what the damping of the system is. And you can also, obviously, if you've got omega n and you've got theta, you can obviously work out where your poles are, or what your x and y values of your poles are as well. These x's here represent poles, imaginary poles. Okay, never mind that just now. So the damping ratio factor determines the slope of that sort of exponential there, which all your under-damped systems will decay at. So you can see this is the actual system response, okay, and that decay rate is determined by your damping ratio, as you can see there. So very underdamped systems have a much longer time before they decay, and quite a less underdamped system will decay a lot quicker. That's just telling you that we've already gone over that rise time, peak time. Oh, I don't know, well, you know about peak time, don't you? Peak time's the time to the first peak. Settling time's the time when this is within 2% of a final value. That's it. Done that already. Yeah, you all know that. Right, we'll just skip over that. Right, now these equations you're going to need for your coursework. You don't need to remember them, but you will need to use them. All you do is just plug the numbers in. They are a little bit complicated to use, so you're going to have a look in the book and make sure you get the same answers as some of the other ones that are done there. But you can work out the rise time by using this equation here. The only thing is this gives us a 0 to 100% rise time. So when you're doing your coursework and you get a different number from your calculation as to what's actually measured, just be aware that it might be because it's not from 10 to 90%. Obviously these numbers, that's your arctan function, that's normal pi, that's your damping factor ratio, and that's your natural frequency. And then there's a slightly easier equation for working out peak time. Again, you just need to put these values in and you get them. You wouldn't be asked to remember these, you just need to use them from the book or whatever. Settling time, approximately 4 time constants again. But you can work it out from that actual equation. And then this one's quite a useful one. This tells you how much overshoot you're going to have depending on your damping ratio. Yeah, which I did say was determined by the exponential decline is determined by the damping ratio. So you can obviously work out the overshoot that way as well. So I would suggest you do some practice with these sort of equations and make sure you can put the numbers in correctly and get the right answers. Because they're not easy. Right. That's just what I've just told you already. Let's get that. This is showing you a wee bit more about what you can actually get from the pole zero diagram. So this line here is a line of constant peak time, as is that one, a different peak time. These lines here are lines of constant settling time, and these diagonal lines are lines of constant overshoot or constant zeta. The diagonals. So there are a few different things you can get from the pole zero diagram. Do we need to know that? Probably not. We'll just skip that. Enough of that. That's just what they've already said, that's like a line of constant damping ratio. There's your diagonals there. Okay, that's the end of that. But the other thing I wanted to just quickly do today was to go over the coursework again, just explain a wee bit more about it. Is that okay? And I'll try and get the rig set up. We might have a break or something. I might have to try and find Dale to see what's wrong with the rig. And I know what's happened. Usually we use the computer for the logging and the laptop for the control, but the computers don't have the software on them anymore, so we had to use the laptop for the control and the logging, and I think there's an address incompatibility in that the logging's trying to write to an address that the controller needs, so the two things don't work together, but I'll see if I can figure it out. Right, coursework. I'm just going to give you a few wee hints about the coursework. You've got to do the coursework yourself. I'm not going to do it for you. So if you open this data, I think you've got let me do that from here. I don't know, has anybody had a look at this already? You've had a look at it, yeah. Okay. So if you open this data, eventually, this data was actually taken by logging what the Bitronic rig was doing. So we took measurements of the level in 1 second intervals. There's a level sensor in the top tank there. But we took them, 1,000th of a second intervals. So what we ended up with was a huge amount of data in here, which is quite a lot. You can actually import that into MATLAB as it stands. I'll show you how to do that. But you do end up, it takes a long time because there's a lot of data. So what I would suggest you do is reduce the amount of data initially by using something like the offset function. Okay, so you can look that up for yourselves in Excel. There's a few different ways of doing this, and it's really up to you what you want to do. But, the way I did it was I used the... it doesn't let me write on that. I used the offset function. Right, so that's in Excel. And what you do is you pick a reference cell, and then you pick an offset value of rows and columns, and then it'll take the answer from each. So every 100th row or every 10th row or whatever number you choose, yeah? So that will reduce your data set quite a lot. You can import that into MATLAB with the XLS read function. So again, you'll need to look in MATLAB itself and get some help, but I think if you want to just do a single whole file, it would be something like that, but you can also reduce it down to a worksheet or a column.
XLS read.
Yeah, sorry, the word's gone a bit out of color. XLS read does that. What I would suggest you do is, rather than try and read from the original data set, is copy your reduced data set and save it as just values. So you know if you use equal sign and you do a copy in Excel and paste, you end up with still getting the entire equation in the background. But if you do a copy as values only, you'll just get the numbers. And I think that would be a better thing to import into MATLAB. Yeah, I think if you import the equations, it might not work very well. So when you've done that, you want to save as values or copy as values. Okay, and you might want to define what column you want as well. So you do that with like a column. So you've got file name. I'm trying to remember. You have to look this up, but I think it's worksheet name. And then you can also have column. If you want a whole column, you probably want to do something like that. E to B. And that'll do the whole column for you. So that's this first starting point. You can also obviously do your graph in Excel. Use scatter plots for your graphs. What you're trying to do is see whether your graph that you produce from the data matches your model's graph when you produce your model. So you will have to graph them both, yeah? Okay. Oh, sorry, there should be a bracket closed at the end of there, but I'm sure you know that. I'm trying to think what else you need to be able to do. Let me just open the course book again. Oh, in fact, if I open this has got some commands here that are quite useful, I think. This is all under the assignment part A. So I would suggest you use it by looking at the data and working out whether it's a first order, second order damped or whatever kind of function. Don't do it that way. That's too difficult. Some of those Castle people did it that way last year, but it's pretty hard. Okay, well, there you go. There's the main commands here. So we've got, you can read the data. You can set up a data variable. If you want to do it this way using the Systems ID toolbox, your data needs to be in a sort of data variable set. It doesn't need to just be read in. So you'd have to set up a data variable using this sort of command here, where y is your level values, u is your inputs. So going back to your Excel data here, you could add another column with your inputs. Your input was a step from 0 to 8. So in terms of what you would do, you would just type in 0 here, and then maybe 8 in the next bit, and then just copy that down. And that column would form your input, yeah? Okay, you get the idea? So if you want to do that ID data thing, you'd have to do it that way. T is your time step, so that'll be determined by what you've chosen as your offset. So if you've chosen an offset of 1,000, your time step is 1 second, since we took the readings every 1,000 of a second. If you chose your time step as 100, it would be a different value. So that's what you put in there, and that creates your ID data thing. And then further down here, this here will estimate a transfer function for you based on the data. Okay, so you can do it manually by looking at your graph, trying to work out what k and what tau is, or if you think it's second order, working out k, omega n, and zeta from the graph. Or you can do it by getting MATLAB to try and do it for you. It'll do something quite similar, but you can use this to do that, but you do have to have the data in this form. Plots, probably most of you already know how to do plots, you just do that. If you want a different figure, you can put figure brackets and the number of figure you want. What else? And then you can do some tests. It's up to you if you use MATLAB for this or Simulink. I would say Simulink is probably easier. Once you have your transfer function, you can just build it as a block in Simulink. And then I think most people know how to put an input, like a step and a scope, or a control systems analysis input and an output to see how it responds. So I think maybe that's easier than trying to do it in MATLAB. You can actually do it with commands as well, but it's not so visual. Okay, I think that's probably it. You do have some lag time, and again, that's more easy to model than Simulink. Modeling lag time with MATLAB is pretty tricky. In fact, I'm not even sure I know how to do that. So a Simulink model would be easier, because you can get just a transport delay block and put your lag time in there. So that's probably easier. And it'll also come to being easier. I think you have to do a PID controller. I'm trying to remember. Do you? Yeah. So again, that's easier in Simulink, because all you do is fit your controller in, add your feedback and your error detector, and then you can simulate that like that straight off. Yeah, I think it's a bit easier. The commands in MATLAB are a bit more tricky. But you will certainly need MATLAB to start with, either to estimate your function or to read in the data. Okay, any questions about any of that? I think you need to just go and start trying to do it, probably. Okay, we'll call that a day now. What I'll do is I'll turn off the recording. I'll try and set up the rig. You can then go and play with the rig yourselves, see if you can replicate the experiment. I'll maybe do a quick demo just to show you what I did. But you're certainly welcome to play with the rig yourselves, if I can get it working. And then you can get on with your coursework. There are assignments for this week as well, as always, in the assignments folder. We're on week 3. So this time I think I'm assuming that you have the book by now, so I haven't given you, I have given you answers, right? But you should have the book by now, so I haven't given you the questions. But it's just these questions here. Anyone have any problems with last week's questions? Managed them okay? Did you even try them?
No.
Okay, that's fine then. So I've got the answers for this week's ones, if anyone gets as far as doing that as well. The answers are there anyway. I think most of the answers are quite straightforward for this week's ones anyway. Okay, that's all for just now then. So, bye to anybody's listening.
This call has been disconnected. Thank you for joining.